This chapter discusses the modeling of this transaction and the principal risks assumed by each party. Much of this discussion reflects the published criteria of the credit rating agencies, but in most instances, these are founded on common sense and should raise no surprises. It goes without saying that in the limited time we have, we can only address a fraction of the analytics necessary for a comprehensive evaluation of all risks in the transaction. We will, however, touch upon each of the major issues. It is useful first to specify the remaining data we have left unstated so far. This is provided in the table you see here. The items shown in red are not inputs per se, but rather are direct consequences of some of the other items. For example, the $20 million notional amount of each reference obligation or exposure is simply the $4 billion aggregate allocated equally among the 200 reference entities. Similarly, the $12 million deemed loss following a credit event is derived from the calculation $20 million notional amount of each exposure multiplied by 100 minus the recovery value, and so on. The premium of 108 basis points under the mezzanine CDS also derives from other items, but is a little more complicated to calculate. This premium, denoted here by the letter P, must be sufficient when added to the LIBOR coupons received on the collateral to enable the SPV, for as long as no losses have been passed on to the investors, to pay LIBOR plus the appropriate spread on all four classes of notes in the aggregate. A little moment of thought reveals that this premium can therefore be calculated in basis points as shown at the bottom of the slide. Thus, P equals 90, the principal of the Class A notes, times 25, the spread over LIBOR of those notes, plus 60, the principal of the Class B notes, times 50, the spread over LIBOR of those notes, plus 70 times 100 for the Class C notes, plus 60 times 300 for the Class D notes, divided by 280, being the aggregate amount of all four classes of notes in total, equals approximately 108 basis points. You should click the pause button until you are fully satisfied with all these calculations. Our analysis now turns to an evaluation of the portfolio credit quality. The pie chart you see here provides a breakdown of the exposures by industry group, the main point being to emphasize the reasonable industry diversity of the portfolio across these groups. Note, however, that some industry groups represent 10% of the aggregate portfolio, such as electronics and finance, towards the bottom left of the pie chart. which would cause severe losses to the portfolio if the entire industry were to undergo a dramatic collapse in credit quality. Little can be done to mitigate this exposure concentration, since the credit rating agencies, and Wall Street as well, typically recognize some 30 or 40 distinct industry groups only, and large bank exposures are not equally distributed among them. It should also be noted that individual exposures of $20 million may appear small in relation to the entire portfolio. Specifically, they represent only 0.5% of the aggregate portfolio, but are not so small in comparison to the amount of total subordination benefiting the lower classes of notes, such as Class D and Class C. Mitigating to a significant degree the concentration risks discussed above is the high credit quality of the reference entities. The bar graph you see here summarizes the credit ratings of the reference entities and should provide significant comfort regarding the portfolio's expected performance over a 3-year horizon. You should readily see that the weighted average credit rating of the portfolio appears to be around BBB+, and this can be confirmed using standard rating agency calculations. The portfolio's expected loss is typically estimated by associating with each reference entity some number for the probability that it may default during the life of the transaction, equal to the average 3-year default probability derived from historical studies published by the rating agencies. For unrated portfolios, it is common to rely on the bank's internal estimates of default probability, which in any event are often modeled largely in conformity with the criteria of the rating agencies. We now illustrate the calculation of the portfolio's expected loss. These calculations are not difficult. Taking, for example, the single A category, the calculation involves the multiplication of the 3-year default probability associated with this category by the portfolio percentage that this category represents. And the results for each category are then added together to find the portfolio expected default rate. This number is then multiplied by the 60% deemed loss percentage per default to derive the portfolio's expected loss. This 0.202% expected loss figure would initially give great comfort to the various note holders, since the subordination amounts from which they benefit is several multiples of the expected loss figure. Thus, for example, the Class A notes, which in aggregate benefit from $230 million, i.e. 5.75% of subordination, would, under this analysis, experience a loss only if the actual loss experience of the portfolio exceeded the expected loss by more than 28 times, a number you can derive by simply dividing the total subordination for this class of 575% by the portfolio expected loss of 0.202%. Even the Class D notes, which absorb losses as soon as the $40 million threshold is exceeded, are exposed only to scenarios that represent an almost 5-fold multiple of expected loss. And yet, this analysis provides an exaggerated sense of security due to one important limitation: the relatively high dollar amount of individual exposures, from which we previously calculated a $12 million deemed loss given the 40% assumed recovery. To be specific, it would take only 4 credit events to erode entirely the $40 million threshold and cause a partial loss to the Class D notes. This number could even diminish to 3 credit events if a lower recovery than 40%, e.g. a 20% recovery, were to result from the bidding process that follows a credit event. These scenarios cannot be dismissed too quickly, given the sizable industry concentrations and the possibility of low recoveries for certain highly leveraged entities, as events during the subprime crisis confirmed in several instances. More generally, we can depict, by means of the table you see in front of you, the point at which each layer begins to absorb losses, subject to our usual assumptions that each loan exposure represents 0.5% of the total portfolio, and that recovery values following a default are indeed 40%. For example, if 9 defaults occur over the life of the transaction, i.e. 4.5% of the entire portfolio, we would derive an aggregate portfolio loss of 2.7% after allowing for recoveries. This would destroy the first loss layer and the Class D notes entirely, and leave a little more of these losses to be passed on to Class C, whose subordination is only 2.5%. Similarly, given the $40 million subordination benefiting the Class D notes, the first 3 portfolio defaults, which would represent $60 million of exposures, would lead, after recoveries, to aggregate losses of $36 million, which would all be absorbed by the first loss layer. Only the 4th default, therefore, would cause a loss to the Class D notes. Note the very high number of defaults needed to pass on losses to the higher rated tranches. By now, we have made solid progress in coming to an understanding of the transaction's key structure and the tranching and subordination, but nothing so far has been done to estimate the likelihood that any specified scenario may occur, only its consequences. So our analysis must now turn to a derivation of scenario probabilities. Our next task, therefore, will be to derive the probability of multiple defaults in a portfolio whose reference entities have a known individual default probability. We begin on the slide with a simple example and proceed after that to one that reflects more accurately the transaction we are examining. This worksheet, labeled Binomial 1, provides a complete probability distribution for a portfolio consisting of 4 entities only. Assumed, for the sake of simplicity, to have exactly a 1% individual default probability, a number that would in fact be a conservative estimate of the 3-year default probability for BBB entities. The label binomial refers to the fact that this methodology describes combinations of scenarios that involve, in the case of each entity, one of 2 possible outcomes: default, for which the probability is assumed to be 1%, or survival, for which the probability would logically then be 99%, with nothing else in between. We will illustrate only the calculation in cell E8, which can then be extended to that in any other cell in column E. In this cell E8, we are calculating the probability that exactly 3 defaults occur, no more nor less. The 1% individual probability of default, appearing in cell F14, is therefore raised to the power of 3, hence the reference to cell D8. Since this scenario requires the calculation that 3 entities jointly default within the designated time frame. This is next multiplied by the 99% survival probability of the 4th entity, hence the reference to F15, raised to the power 4 minus D8, which comes out to 1, confirming that we are dealing with only one survivor here. The last part of the formula, where you see the combin operator from Excel, recognizes that there are several combinations of defaults that would fall under this scenario. If, for example, we label our 4 entities A, B, C, and D, we can list 4 combinations that describe a scenario of 3 defaults and 1 survivor: ABC, ABD, ACD, and BCD. More generally, you were probably taught in high school the general formula for calculating the total number of ways of selecting R entities out of a total of N entities from which to choose. NCR, the notation, is defined to equal N factorial divided by R factorial times N minus R factorial. a formula that is programmed into the Excel operator combin. Important limitations to the application of this methodology to a real-life CLO would include the following. The mathematics we have described above assumes that the entities have zero default correlation with each other. This is a critical point. Defining default correlation has proven tremendously difficult for the financial industry, but we can loosely think of it as the tendency of two entities to default together. The more these entities have in common, such as their underlying business model, geographical reach, customer base, leverage ratios, quality of management, and so on, the more we would expect them to experience distress together when conditions are difficult, and therefore the more we would anticipate that if one of them defaults, the other one would probably default as well. This explanation is sufficient for our purposes. The main point to extract from it is that the further default correlations within a portfolio increase, the less accurate our binomial model becomes for estimating joint default probabilities. Modeling the default probability distribution for a portfolio of exposures that have significantly positive default correlations is generally done by means of a technique known as Monte Carlo simulation, a topic beyond the scope of this module. Furthermore, the binomial methodology requires that the default probability of each obligation is constant across the entire portfolio. This is one of the main reasons it is common to pool together in CLOs exposures that have approximately the same credit quality. Lastly, variations in the individual default probabilities will cause corresponding variations in the probability of each scenario in our previous table. Increases in individual default probabilities will cause an increase in the probability of each scenario, except, logically enough, the scenario involving zero defaults, whose probability would diminish, and vice versa. This last point can be demonstrated by returning to worksheet binomial 1 and simply modifying the input in cell F14. Thus, an increase to 5% in this input can be seen to increase the probability of each scenario except the one in the bottom row representing the zero default scenario, whose probability has diminished substantially. And vice versa, if, for example, we reduce the individual default probability to 0.1%. Caution should be exercised when we use portfolios with hundreds of entities or with very high individual default probabilities. But otherwise, these general rules work well. We can now expand our analysis to the actual portfolio in our discussion, which has 200 entities instead of just 4. And we do this on worksheet binomial 2. This worksheet is far larger, obviously, than the previous one, but the formulas behind the cells are identical to the ones before. Note, importantly, that we have hidden many dozens of rows representing scenarios for which the probability is visibly 0. A quick glance at this worksheet reveals a number of key observations. First of all, scenarios representing 13 defaults or more have 0 probability, at least to the 4th decimal point of accuracy. We remind you, however, of the critical assumption that default correlations in the portfolio are 0, which is unrealistic. Subject to this and to our other assumptions, we can now understand quite easily why the senior classes of SPV notes have such a high credit rating. A second observation is that with as many as 200 entities in our portfolio instead of just 4 on the previous worksheet, the scenario describing 0 defaults in the portfolio now has a probability of only 13.4%, down from 96% on the previous worksheet. Thus, it is almost certain that some portion of the $40 million loss threshold will be absorbed by Bank ABC. A final observation for now is that scenarios involving 7 to 12 defaults have an aggregate probability of well below 1%. The figure we have been using for the 3-year default probability of BBB rated instruments. Since those scenarios are the ones that would pass losses through principally to classes C and D of the notes, we can now understand why even those classes have ratings that are investment grade, or nearly so in the case of Class D.